All right, so we got Chapter 4 homework. You ready to go?
Yeah, I'm ready.
All right. In what smallest whole number ratio must nitrogen and oxygen atoms combine to make nitrogen tetraoxide?
You mean like 2 nitrogens for every 4 oxygens?
That's right. That's what we want to recognize. When we see a chemical formula like this, it's telling us that there's 2 nitrogens for every 4 oxygens. What's the mole ratio of the elements in this compound?
Mole ratio?
That's exactly right. So remember, the term mole essentially is saying a given amount of that substance. And we use the term mole in chemistry. It's kind of like a shortening of the term molecular ratio. So 1 molecular unit of nitrogen compared to, 2 molecular units of nitrogen compared to 4 molecular units of oxygen. So the mole ratio of the elements in this compound is also 2 to 4. The atomic ratio, 2 atoms of nitrogen to 4 atoms of oxygen. But we can also say 2 moles of nitrogen for 4 moles of oxygen. Okay? Now, if the word mole bothers you, just use the word dozen in its place. So just like you would say 2 atoms of nitrogen for every 4 atoms of oxygen, you could get its same ratio by saying 2 dozen atoms of nitrogen or 2 dozen nitrogens for 4 dozen oxygens. All right? So again, the mole is just a number that has a name, like dozen.
Okay.
So, how many moles of tantalum atoms correspond to 1.56 times 10 to the 21 tantalum atoms?
I don't know what this means.
Well, essentially, we're trying to remember that the mole is a number. Do you remember what the number for the mole is?
I don't.
The number for the mole is 6.02 times 10 to the 23rd. All right?
How did we get that number?
That's the number of atoms of carbon that are in 12 grams of carbon. And because element carbon is 12 times heavier than the lightest atom, or pretty close to 12, we defined 1 mole of a species as 12 grams. 1 mole of carbon is 12 grams of carbon. Then we found out how many atoms there were in 1 mole of carbon, or 12 grams of carbon. So this is how many atoms of carbon there are in 1 mole of carbon, which is 12 grams of carbon. So all those are the same. Now, once we found that out, then we said, okay, how many grams are there in 1 mole of atoms of other elements, right? And those numbers are what are included on the periodic table down here. So if we look at any one of these elements, aluminum, 26.961539, that begins to be the mass in grams that you need to have of aluminum if you want to have 1 mole of aluminum. Okay? So what that's done for us, by defining 12 grams as 1 mole of carbon, as this many atoms of carbon, we can use the units of grams per mole for every single one of these elements, right? If I want a mole of fluorine, how many grams do I have to weigh out? This number. If I want a mole of copper, how many grams do I have to weigh out? That number. That number has the units of, that's how many grams you need to get 1 mole. Now in this case, we're asking for how many moles of tantalum atoms. So I can write to my equal sign here, moles of tantalum. If I start off with, how many? 1.56 times 10 to the 21. This is atoms of tantalum. Let's see, tantalum is TL. All right. And now, if you have a number of, if you have 6.02 times 10 to the 23rd of anything, you have a mole of it, right? Because that's just a number. So what we would do here is we say 6.02 times 10 to the 23rd atoms of tantalum. That's the same as 1 mole of tantalum. So we use this. Do you remember what you call that?
You mean like a conversion factor?
That's right. It's a conversion factor. It's telling us how many of atoms of tantalum there are in a mole of tantalum. Okay? And that could be, you know, anything. This is how many dogs are in a mole of dogs, right? So again, the mole, the term mole, is just a number, and 6.02 times 10 to the 23rd is that number. So 1.56 times 10 to the 21 divided by 6.02 times 10 to the 23rd. Atom of tantalum get canceled out, and my answer is in moles of tantalum. Okay, so let's see if we can get that. 1.56 times 10 to the 21. All right, that's what it should look like in your calculator. And I like to push enter so that I give the calculator clear direction in terms of order of operation. And then we divide by 6.02 times 10 to the 23rd. Whoops. I pushed it twice. Let's get rid of one of these. Delete. There we go. So it's 0.0025 to 259 really moles of tantalum. Okay, so essentially what we did is we were told how many atoms of this material we had, and we know that there's this many atoms in 1 mole of the material, and we could identify how many moles. Okay, good. All right, so sucrose, table sugar, has that chemical formula, and we want to know the ratio of carbon to hydrogen atoms. What do you think?
Atom ratio and mole ratio, is that different?
It's not. It's not different, and that's what we're trying to recognize, that we can say that there's 12 to 22, right? 12 to 22 carbons to hydrogen. And if we wanted to simplify that, I guess we divide by, what? 2 would give us 6 and 11, right? If we divided that by 2. So 6 carbons for every 11 hydrogens, right? That's our ratio there. And that would be also 6 moles of carbon to 6 moles of hydrogen. For hydrogen to oxygen, what's that?
2 to 1 for hydrogen and oxygen.
Very good. And that's the atom ratio. What about the mole ratio?
That's the same?
That's right. Good. So what about carbon to oxygen? What's the mole ratio?
There's 12 carbon to 11 oxygen, and you can't simplify that, right?
That's right. Very good. Excellent. So how many moles of bismuth are needed to combine with 1.58 moles of oxygen atoms to make bismuth oxide?
Moles of bismuth. So it's 2 to 3 moles of bismuth per mole of oxygen.
Very good. 2 moles of bismuth for every 3 moles of oxygen, right? We got that from the chemical formula here, right? So now what?
And they're saying we have not 2 moles of oxygen, but 1.58?
That's right. So we have 1.58 moles of bismuth, and we can say that this ratio has to be the same, so we could find out X moles of oxygen there. That's one way to do it. The other way to do this is to write, to the right of our equals sign, moles of bismuth, and say that we've, wait a second, how many moles of bismuth are needed to combine with 1.5, oops, I put the 1.58 in the wrong spot here. This 1.58 moles of oxygen would go here, and we'd be solving for moles of bismuth up there. So the other way to do it again, see, and that's the danger of this because we wrote it down wrong. But anyway, moles of bismuth here, and then we start with 1.58 moles of oxygen. And then we relate moles of oxygen to moles of bismuth with this 2 to 3 here. 2 moles of bismuth for every 3 moles of oxygen. So 1.58 times 2 divided by 3 should be our answer for the moles of bismuth. That make sense?
Yeah, that makes sense. We already know the ratio from the chemical formula, 2 to 3, and then we can use that ratio of unknown amount of bismuth for every 1.58 moles of oxygen.
Yeah, right. Good. So how many moles of chromium are there if I have 2.16 moles of chromium 3 oxide? Is this chromium 3 oxide?
I think so. If you use the reverse crisscross, yeah, reverse crisscross, the 2 goes, yeah, so it's chromium 3 oxide.
Very good. This is a mix of chromium 3 ions and oxide ions. There's 3 of these oxide ions, 3 of these oxide and 2 of these chromiums, right? And we see that they both add up to 6, positive 6 and negative 6. So how many moles of chromium, that's a little review there, how many moles of chromium are in 2.16 moles of chromium 3 oxide? Well, if we use the equal sign, what do we put to the right of the equal sign?
Moles of chromium is what we're after.
Very good. So you want to be specific, moles of chromium. And we start with what?
2.16 moles of that stuff.
That's right, 2.16 moles of Cr2O3. And then down here, what do we want to have?
I don't know.
Well, I always want to get rid of my units up here, right?
Oh, yeah, so moles of chromium oxide.
Good. Moles of chromium, chromium 3 oxide. Very good. And up here, can I relate that to moles of chromium?
What do you mean?
Well, see, moles of chromium here, moles of this stuff. Do we know how many moles of chromium there are for every mole of that chromium 3 oxide?
Oh, there's 2.
That's right, 2 moles, right? 2 moles of chromium for every 1 mole of that material. So the 2.16 times 2 should give us our answer there. Got it?
Yeah, okay.
All right, so aluminum sulfate. Construct a pair of conversion factors that relates the moles of aluminum to the moles of sulfur for this compound.
Conversion factor that has moles of aluminum and sulfur. Let's see. There's 2 moles of aluminum for every, how many moles of sulfur in that thing? Just 3, right?
That's right. So that's a good conversion factor. 2 moles of aluminum for every 3 moles of sulfur. Now, do you understand how he did that?
I think so. Why don't you tell me to make sure?
Okay. So what we have here then is a chemical, Al2SO4-3, and for every 1 mole of this stuff, there's 2 moles of aluminum. Do you see that?
Yeah, I see that. 2 aluminums in there.
And for every 1 mole of this stuff, there's also how many moles of sulfur?
Every 1 mole of that stuff has 3 moles of sulfur.
That's right, 3 moles of sulfur. So you can also use this as a conversion factor, which is what we have. You could also, construct a pair of conversion factors. And what we're trying to emphasize here is you can go 2 moles of aluminum for 3 moles of sulfur, but you can also go 3 moles of sulfur for every 2 moles of aluminum. Right, another conversion factor. Okay, good. How about the next one? Moles of sulfur to moles of that stuff.
Well, we already did that, didn't we?
We kind of did, right? So let me bring that back up here. I have 3 moles of sulfur for every 1 mole of this material, or we could flip it around. Every 1 mole of this material has 3 moles of sulfur, right? So you can flip them either way. How many moles of aluminum are in a sample of this compound if the sample contains 0.9 moles of sulfur?
Moles of aluminum. That's what we want, right?
That's right. So that goes where?
To the right of the equal sign.
Very good. We get an equal sign and we say moles of aluminum. Very good. What do we start with?
0.9 moles of sulfur.
Very good. They gave us 0.9 moles of sulfur. And now I need to relate moles of sulfur. I need the moles of sulfur to drop out, and I need to go to moles of aluminum. All right, now what was my conversion factor?
There's 3 moles of sulfur and 2 moles of aluminum.
Very good. So 0.9 times 2 divided by 3 will be the moles of aluminum there. How many moles of sulfur are in 1.16 moles of aluminum sulfate? So this is part C here. And now we're working on part D. What goes to the right of our equal sign?
Moles of sulfur.
Very good. Moles of sulfur. And what am I starting with?
1.16 moles of aluminum sulfate.
1.16 moles of Al2SO4-3. And then I just need to relate moles of aluminum sulfate to moles of sulfur.
Yeah, and there's 2, right? No, 3.
That's right. 3 moles of sulfur for every 1 mole of aluminum sulfate. So 1.16 times 3 is going to give us our answer there. Okay, good job. How many moles of H2 and N2 can be formed by the decomposition of 0.145 moles of ammonia, NH3?
So, I don't know. Do we need an equation?
Well, we don't necessarily need an equation. We could just think of this, NH3. If this is going to create some N2, how many N2s am I going to get for every one of these? Can you see that?
Not really.
Well, I have 2 nitrogens in N2, and I only have 1 nitrogen in NH3. So it's going to require 2 NH3s for every N2. Now, this isn't a balanced statement. It's just recognizing that if I'm getting out N2, then I'm going to need 2 of these for every N2 that I get out. Do you see that?
Oh, okay, I guess.
But it might be easier just to kind of write an equation in which we show the decomposition of NH3 into N2H3, and then we can say we're going to get, no, not 6, but 3 H2s for every 1 N2, right? So there's our balanced equation. And then we can just say moles of hydrogen. We're looking for moles of, not hydrogen, but hydrogen gas, moles of nitrogen gas. And we got 2 NH3, no, sorry. What do we start with?
0.145.
0.145 moles of NH3. And then we go from moles of NH3 to moles of hydrogen here. And this one here, we start off with the 0.145 moles of NH3. And we go from moles of NH3 again to moles of nitrogen gas. All right, so what's the ratio? How many moles of hydrogen do I get for every mole of nitrogen?
2 moles of nitrogen.
Yeah, see, that's what the equation tells me, right?
And 3 moles of hydrogen.
Very good. So 2 moles of ammonia go in and 3 moles of hydrogen gas come out. This one down here?
That's 1 to 2.
Very good. 1 mole of nitrogen comes out for every 2 moles of ammonia that goes in. Okay, so 1.45 times 3 divided by 2, that's how I get the hydrogen. 0.145 times 1 divided by 2, that's how I would get my moles of nitrogen. Okay, good. All right, so how many moles of UF6, uranium hexafluoride, would have to be decomposed to provide enough fluorine to prepare 1.25 moles of CF4? So, if I need CF4, how many fluorines do I need for every CF4?
One of those has 4 fluorines.
Very good. One of these has 4 fluorines. And UF6, whoops, how many fluorines does one UF6 give me?
Well, UF6, if you took the fluorines, you mean?
Yeah, if I took all the fluorines off of here to make fluorines here, or put the fluorines on the carbon, how many would I get when I take them off here?
6.
Yeah, I'd get 6 here, and I need 4 there. So for every one of these, I get 6 moles of fluorine, and for every one of these, I need 4 moles of fluorine. So how many of these would I need if I want to get 1.25 moles of CF4?
I'm not sure.
Well, do you know what they're asking? What goes to the right of the equal sign?
It says moles of UF6.
Very good. So we can just start with that. Moles of UF6. And what can I start with here?
Is that the 1.25 moles of CF4?
That's right. 1.25 moles of CF4. Okay. And essentially, I need to relate the moles of CF4 to moles of UF6. All right?
Well, I'm not quite sure.
Well, maybe if we do it this way, maybe if we take moles of UF6, 1.25 moles of CF4, and maybe if we go from moles of CF4 to moles of F.
Why would we do that?
Well, because then we can identify how many moles of F are necessary to get moles of UF6. Right? Because for every 1 mole of UF6, I need 6 moles of fluorine. There are 6 moles of fluorine.
Okay.
And for every mole of CF4, I get 4 moles of fluorine. You see that?
Okay, I see. So you got 1.25 moles of CF4 that you want to get, and that means you need 4 moles of fluorine. And you get 6 moles of fluorine for every UF6.
Very good. So 1.25 times 4 divided by 6 gives me my answer there. Okay, good. Okay, so how many atoms of carbon are combined with 4.13 moles of hydrogen atoms in a sample of the compound propane, C3H8? That's what we use in barbecues, right? Propane gas. So what goes to the right of the equal sign?
How many atoms of carbon?
Very good. Equal sign, atoms of carbon. Starting with what?
4.13 moles of hydrogen atoms.
Okay. 4.13 moles of hydrogen atoms. Very good. So, if I want to relate moles of hydrogen atoms to moles of, well, they're not. We're not asking moles of hydrocarbon. We're asking just atoms. So we need to go to moles of carbon atoms first, and then we can go from moles of carbon atoms to moles of, or just to atoms of carbon. Do you know how many atoms of carbon are in a mole of carbon?
How many atoms are in a mole?
Yeah.
Is that big number?
Yeah, that's right. 6.02 times 10 to the 23rd atoms for every mole of carbon. Now, what about this? Do you know how many moles of hydrogen relate to moles of carbon in our compound?
Is that 3 to 8?
Very good. 3 what?
C3H8. So 3 carbons to 8 hydrogens.
Very good. We know this ratio from the chemical formula there. So for every 3 moles of carbon that we want to have with hydrogen, it requires 8 moles of hydrogen, right? And then we're in moles of carbon there, and for every moles of carbon, we're going to need that many atoms of carbon. So 4.13 times 3 divided by 8 times that big number, Avogadro's number they call it, and that is our atoms of carbon. Good. What's the total number of carbon, hydrogen, and oxygen atoms in 2.60 moles of glucose?
Whoa, that's a lot, right?
Yeah, so what goes to the right of our equal sign? What are we looking for?
Total number of carbon, hydrogen, and oxygen?
All right, so I kind of think that this needs to be 3 separate problems to simplify it for ourselves. So we want carbon atoms, hydrogen atoms, and oxygen atoms, and then we'll just add them up at the end. Okay? There's another way we could do it. We could say just total atoms, and that would be just as easy or fine. And maybe we'll do that afterwards. But if we start with 0.260 moles of glucose, is that right?
Yeah, 0.26 moles of glucose, C6H12O6.
Very good, C6H12O6. So, moles of glucose, I want to relate that to not atoms of carbon directly, but moles of carbon first.
Okay.
So I go from that to moles of carbon. How many moles of carbon for every mole of that material?
6 to 1.
Very good, right? Because it says there's 6 carbons. Okay? So you can see that each one of these is going to have to be 0.26 moles of that material, right? For every mole of hydrogen, it's 12 for every one of the C6H12O6. This one here, oxygen, is going to be 0.26 6 moles of C6H12O6. And for every 1 mole there, 6 moles of oxygen, right?
Yeah, okay.
C6H12O6. All right. Let's focus on the top one here, finish it up. If I want to go from moles of carbon to atoms of carbon, I need to use what number?
That Avogadro's number.
Very good. 6.02 times 10 to the
23rd.
Very good. For every mole. Okay, so that tells me how many atoms of carbon. All right. And then the same thing here. I would go 1 mole of hydrogen, 6.02 times 10 to the 23rd atoms of hydrogen. 1 mole of oxygen, 6.02 times 10 to the 23rd atoms of oxygen. So I solve for all 3 of those. 0.26 times 6 here, times that Avogadro's number. 0.26 times 12 times Avogadro's number. 0.26 times 6 times Avogadro's number. Right? Okay. The other way to do it will be just kind of exactly the same, but all in one, where we go for moles of all the atoms, for example. And we start off with 0.260 moles of C6H12O6. And then I could go from moles of C6H12O6 to moles of atoms, right? And then I could just do 12 plus 6 plus 6, 24 moles of atoms. And then I could go, if I have 1 mole of atoms, I have 6.02 times 10 to the 23rd atoms. So 0.26 times the 24 times that would give me the moles of all the atoms, right? Good. All right, so how about this one? How many atoms are in 6 grams of carbon-12?
Could we put the atoms at the right of the equal sign?
Yeah, that seems to be very easy, right? What is it? How many atoms? So number of atoms are in 6 grams of carbon-12. So if I have 6 grams of carbon, right, how many atoms do I have?
Well, you go from grams of carbon to moles of carbon.
Very good. Now, the nice thing about going to moles of carbon, it's always nice to go there because then we can relate moles to Avogadro's number, 6.02 times 10 to the 23rd. Right? But do you know how many grams of carbon are in a mole of carbon?
Isn't that on the periodic table?
That's right. It is on the periodic table.
12.01.
That's right. 12.01. Now, that's 12.01 if it's what an average carbon atom weighs. That means some weigh 12, some weigh 13, some weigh 14. This is saying of carbon-12, so it's 1 mole of carbon-12 is 12 grams. So essentially what we're doing here is, because 6 is half of a mole, it's just Avogadro's number divided by 2. 6 times Avogadro's number divided by 12. Okay, good. Okay, 4.49. Determine the mass in grams of each of the following. 1.53 moles of iron. All right. So what is it we're asked to find here?
Mass in grams.
Okay. Mass, grams of what?
Grams of iron.
That's right. Grams of iron. So grams of iron to the right of our equal sign. If we start with 1.35 moles of iron, where are we going to go from there?
Well, moles of iron are down below.
That's right.
And
all right, so can I go from grams of iron to moles of iron?
yeah, that's just the periodic table, right?
That's right. On the periodic table, this number, right, tells me how many grams, 55.847, are in 1 mole. So there's 55.847 grams for every 1 mole. So now 1.35 times the 55.847 should give me my grams of iron. All right, how about grams of oxygen, starting with 24.5 moles of oxygen? What goes down here?
How do you know what goes down there?
Well, you're trying to get rid of these units here and go to those units there. So if I divide by those units here, right, we always put those down there, that gets rid of them. And then if I can go to these units, then it's a simple single conversion factor conversion, right? So there's 16 grams for every 1 mole. Does that make sense? So 24.5 times the 16.
Okay. So the last one, we put the grams of calcium to the right.
Very good. Starting with what?
0.876 moles of calcium.
Good. What goes down here?
Moles of calcium. To grams of calcium.
All right. Now how many?
Periodic table, let me see. Is it 40?
That's right. 40 grams per mole. So that times our 40. Okay. Good job. All right. So we need 2 times 10 to the 12 atoms of potassium. And we want to know how much mass we have to weigh out to get that many atoms. So what do?
We want grams of potassium, right?
Yep.
Equal sign.
Good.
Grams of potassium.
Okay, so what do we start with?
2 times 10 to the 12th atoms.
That's right. 2 times 10 to the 12th atoms of potassium. And now, what goes down here?
You need to get rid of the atoms of potassium.
Very good. Atoms of potassium. And I can go from atoms to moles of potassium, right?
Okay, yeah.
How many atoms are in 1 mole of potassium?
I don't know.
Well, remember, a mole of anything, mole of those, how many moles of atoms of potassium is Avogadro's number, right? It's like a dozen, not 12 though. It's 6.02 times 10 to the 23rd. So atoms of potassium can be converted to moles by using Avogadro's number. And then, I'm not quite done yet though.
No, you just got to go from moles to grams.
Good. Moles of potassium down here, grams of potassium there. Can you look on your periodic table? What is it?
Is it 30, does that say 39?
Let's get a little bit bigger. $39.1. Yeah, 39.1. Is that right? Yeah. Okay. Grams per mole. So 2 times 10 to the 12th divided by 6.02 times 10 to the 23rd times 39.1. And that'll tell me how many grams of potassium I need. Okay, very good. All right, how many moles of nickel are in 17.7 grams of nickel? That's easy, right?
Yeah, moles to the right of the equal sign.
Very good. And not just moles, but what?
Oh, moles of nickel.
Very good. And I start with?
17.7 grams of nickel.
Very good.
And then grams on the bottom.
How did you know grams goes there?
Because you got to get rid of those grams.
That's right. Very good. So then I go to grams to
moles.
And looking at the periodic table, 58.7.
Yeah, 58.7.
Grams per mole. So 17.7 divided by 58.7 will tell me how many moles of nickel I have if I have 17.7 grams of nickel. All right, so now we need to calculate the formula mass for each of the following. Okay? Maximum number of significant figures possible using the table of atomic masses inside the front cover. Yuck. I don't think I'm going to do that. I'm just going to use the maybe 1 or 2 significant figures. Sorry, 2 or 3 significant figures. So, sodium. Well, what's the name of this compound? Do you know?
I don't know what HCO3 is, but Na is sodium.
All right, so how can we figure out?
Do you have that list of polyatomic ions?
Sure do.
HCO3. Oh, there it is. Hydrogen carbonate ion?
Yeah, and I think it's preferable probably to call it the bicarbonate ion.
Okay, bicarbonate. So sodium bicarbonate?
Yes, sodium bicarbonate. That's baking soda. So to find the formula mass, all we have to do is not the atomic mass. For the atomic mass of sodium, we would just look on the periodic table and see the 23 there, right? But this is the atomic, or the formula mass. So I need the atomic mass of sodium, one sodium that is, 23, one hydrogen, H, one carbon, 12, sorry, one hydrogen is 1, carbon, 12, 3 oxygens, that's 48, no, 6, let's see, 16 times 3, yeah, 48. Okay, so 23 plus the 1 plus the 12 plus 48, and then I'm going to get my handy dandy phone here and ask it sorry about this. What's the molar mass of sodium bicarbonate?
The molar mass of baking soda is 84.01 grams per mole.
Okay, so you know when as you move forward in your chemistry experience, you're going to rely on this more than just adding something up. But we can do it really quick here to make sure we're right. 12 plus 1 plus our 16 3 times. There we go. So I got the 84. Okay? All right. So our second one there, what is the name of that compound?
That is, let's see, the polyatomic ion chart. Let me look.
Yeah, everybody at home, try to look and find the name of it too.
Is that ammonium and carbonate? So ammonium carbonate?
Very good. Ammonium carbonate. And how many nitrogens?
2 nitrogens.
Each one's 14, right? So 14 times 2. How many hydrogens?
8 hydrogens.
8 times 1. You know where I got the 14?
That's the mass of a nitrogen on the periodic table.
That's right. So 2 of those. So we're adding up all of our values here, right? 12 and then our 48 again. Very good. So what's the molar mass of ammonium carbonate?
The molar mass of ammonium carbonate is 96.09 grams
So
per
that
mole.
should add up to 96.09. All right. C, do you know the name of C?
Let's see, that's copper, and let me look at the polyatomic ion chart. Sulfate, copper sulfate, and then 5 is, what is 5?
Penta.
Penta, copper sulfate pentahydrate.
Okay, very, very good. Now there's one more thing. Because copper is a transition metal, you want to tell everybody what type of copper you have.
Oh yeah, let's see, sulfate is a -2.
Very good. SO4 is a 2 minus. That's what it says on the polyatomic ion chart.
And there's 1 for every copper.
Very good. So what does that mean the charge has to be on the copper?
That has to be +2.
Very good. So that means that this is copper what sulfate?
Copper 2 sulfate.
Very good. Excellent job. So I got copper 2 sulfate pentahydrate. Molar mass of copper 2 sulfate pentahydrate.
Molar mass of
249.68.
copper 2 sulfate pentahydrate is 249.
Okay. So again, that's what you're going to get if you add up 1 copper, 1 sulfur. How many oxygens?
4.
Are you sure?
Oh, no, there's 9 altogether.
Very good. And how many hydrogens?
10.
Very good. All right, potassium dichromate. What's the chemical formula for potassium dichromate?
Potassium is K.
Okay, good. That's the potassium ion, right?
Oh, yeah, good. Yep. Dichromate, that's on our periodic table, or our polyatomic ion chart, right?
Yep. So let me bring that up for you.
Oh, I see it here. It's Cr2O7.
Yeah, very good. So our dichromate, Cr2O7 with a 2 minus charge, right?
Okay, yeah. So Yeah, okay. So then what?
Well, we have to make sure we bring these together in the right ratio, right?
Okay, I'm going to need 2 potassiums.
That's right. So K2Cr2O7. That's going to be the chemical formula. I find the mass for 2 potassiums added to the mass of 2 chromiums, and 7 oxygens. Molar mass of potassium dichromate.
The molar mass of potassium dichromate is 294.18 grams per mole.
All right, add them together. Make sure you get that value. 294.185. Good. Okay, aluminum sulfate. What's the chemical formula for aluminum sulfate?
Aluminum's Al, right?
Yep.
Sulfate is SO4 2-. That's what my table says there.
Okay. Do you know the charge on the aluminum?
I'm not sure. What is the charge on aluminum?
What does the periodic table help us with that?
Oh yeah, we tried this before. Aluminum, if you gain 1, 2, 3, 4, 5 electrons, but that was too many, you said, right?
Yes, and it's a metal, so it's going to want to lose electrons when it forms ionic compound.
So it's going to have a +3 charge?
Very good. +3. So the chemical formula then is?
If I use the crisscross rule, Al2, SO4, 3 of those.
Very good. Excellent job. So I have to add up 2 aluminums, 3 sulfurs, and 12 oxygens, and that will give me my molar mass for aluminum sulfate. Molar mass of aluminum sulfate?
The molar mass of aluminium sulfate is
342.15.
342.15 grams per mole.
Okay, good job. All right, so we want to calculate the mass in grams of 1.25 moles of calcium phosphate. Okay, so tell me, how do we set this up?
You want mass of calcium phosphate, grams.
Very good. So that goes to the right of the equal sign.
Right. And then you start with 1.25 moles.
Whoops.
Okay, and then you go from moles to grams.
All right. So what are my values? What are my conversion factors there?
You want to convert, you need the molar mass.
That's right. I need the molar mass of calcium phosphate.
The molar mass of tricalcium phosphate is 310.18 grams per mole.
Hey, why did it call it tricalcium phosphate?
Because it doesn't know how to name chemicals. There are a lot of kind of common names that still are around, and you see them in the kind of the media and stuff, but yeah, it doesn't know how to name chemicals appropriately. So 310.18, and that's how many grams I have for every mole. So I got rid of moles, and now I go 1.25 times my 310, and that should give me my grams of calcium phosphate. Okay. The iron 3 nitrate, grams of iron 3 nitrate. Now, do you know what chemical iron 3 nitrate is?
Well, the iron 3, what does that mean?
That means that the iron has a +3 charge in it.
Okay, yeah, and then nitrate is NO3 with a -1, so you must need 3 of those.
Very good. 3 of these NO3 -1s. All right. So there's iron 3 nitrate. And then I can go from moles, 0.625 millimoles. Okay, so that is millimoles. And for every 1,000 millimoles, I have 1 mole. And this is again of my iron 3 nitrate. And then I can go from moles of iron 3 nitrate to grams of iron nitrate. Good job. Molar mass of iron 3 nitrate.
The molar mass of iron 3
241.86
grams per mole.
grams per mole. All right. I did have to go from millimoles to moles, right? Again, this is iron nitrate. Okay, so millimoles of iron nitrate over here cancels out. Moles cancels out. I'm left in grams. So 0.625 times 241.86 divided by 1,000. Okay, good. Let's see. This problem has some other, two other parts to it. Let me get those here. Okay, so again, we're calculating the mass in grams. So how many grams of C4H10? Grams of C4H10, right?
Yeah.
Starting with 0.6 micromoles of C4H10. Micromoles C4H10 to moles of C4H10. Do you know what a micromole is?
Micro, is that 10 to the minus 6?
That's right. So I could go 10 to the minus 6 moles for every micromole, or I could say 1 mole has 10 to the 6th micromoles, right?
Okay.
So that's my conversion factor there. Now I'm in moles of my C4H10, and I can go from moles of C4H10 to grams of C4H10. C4H10, this is what we're going to have to add up, unless you know the name of it. I know the name of it, but I think that most of us aren't going to be able to remember. So we can't ask Google. C4, that's 4 times 12. H10 plus 10. So we got 48 plus 10, 58 grams per mole. All right. So 0.6 divided by 10 to the 6th times 58, and that'll tell us how many grams of C4H10. All right. Excellent. Now we're going to go for, and the last one here, grams of ammonium carbonate. Do you know the chemical formula for ammonium carbonate?
The ammonium ion is NH4, and carbonate is CO3.
Very good. Is that it?
Yeah.
Okay. So, there's one thing missing here. One thing missing. Something wrong with this thing here. Do you see anything wrong with it?
No, that's the ammonium ion and the carbonate ion. That's what it says on the periodic table, or on the back.
Okay. Well, remember, when we look at our ions, we have to look at their charges, right?
Oh, okay, I see what you're saying. You need 2 ammoniums.
Very good. 2 there. Because there's just a plus 1, and that's a minus 2. All right. Would that have changed the answer?
I don't know, would it?
Yeah, it would, because remember, at the last step here, we go from ammonium carbonate from moles of ammonium carbonate to grams. And if we looked up the mass of NH4CO3 as opposed to NH42CO3, it's a different mass, right? Molar mass of ammonium carbonate.
The molar mass of ammonium carbonate is 96.09 grams per mole.
So we go from moles of ammonium carbonate, NH4 to grams, and find out how many grams 1.45 moles is. 1.45 times our molar mass. Okay, very good. Okay, calculate the number of moles of each compound in the following sample. So I want moles of calcium carbonate, right? Now it's important that we find the correct chemical formula for calcium carbonate. Calcium's a +2 ion, right?
Yeah, I know that from the periodic table. Carbonate CO3 2 minus. So it's just a 1-to-1 ratio, right?
That's right. So it's going to be CaCO3. Very good. Now I start off with 21.5 grams. 21.5 grams of CaCO3. And I'm going to go from grams to moles, right? CaCO3. CaCO3. Now I got to find the molar mass. I need to find out how many mole or grams there are in 1 mole. Molar mass of calcium carbonate.
The molar mass of calcium carbonate is 100.09 grams per mole.
So 21.5 divided by our molar mass should give us our moles of calcium carbonate. All right, I want moles of ammonia, NH3, starting off with 1.56 nanograms of ammonia, NH3. Well, I can go from nanograms to grams. There's 1 gram is 1 times 10 to the 9th nanograms. Remember, that's what nano is.
I didn't remember that, but I could go look it up and have remembered.
Good. That's good. Nano is 9. So there's, make sure we put 1 times 10 to the 9th for every gram there. And now we're in grams of ammonia. And we just need to go to moles of ammonia. Do you know how many grams of ammonia there are in a mole of ammonia?
Nitrogen's 14, 1, 15, 16, 17.
17 grams per mole. Good. So 1.56 divided by 1 times 10 to the 9th divided by 17. It'll tell me how many moles. Okay. Strontium nitrate. I need to know the moles of strontium nitrate. I need to know the chemical formula for strontium nitrate. What is it?
Strontium's SR and nitrate's NO3.
Very good. So let's see. What's the ion that strontium makes?
Where is it at on the periodic table?
It's element 38.
Okay, so that's +2.
Very good. And nitrate?
It's on the polyatomic ion. It's a -1. So that's SrNO3 and then 2 of those.
Very good. 2 of those. So I have how many? 16.8 grams of SrNO3 2. I just need to go grams of strontium nitrate. 2 moles of strontium nitrate. Okay. Molar mass of strontium nitrate.
The molar mass of strontium nitrate is 211.63 grams per mole.
Very good. Last one here. Moles of, what is that beast called?
Sodium. Let me look at my polyatomic ions. Oh, that's chromate.
Very good. Sodium chromate. Na2CrO4. Very good. And so I just need to go 6.98 micrograms. I'll go from micrograms to grams and then go grams to mole. Right? Again, this is the sodium chromate. Okay.
What numbers go in there?
Well, what do you think? What numbers go in here?
Micrograms. Micro is 10 to the 6th.
That's right. So 10 to the 6th micrograms for every gram.
And ask your phone what the molar mass of sodium chromate is.
Molar mass of sodium chromate, 161.97.
161.97 grams per mole.
Very good. So 6.98 divided by 10 to the 6th divided by 161.97. Excellent job, Fred.
Thank you.
All right. So we got a sample of calcium carbide, 1.5 moles of carbon. How many moles and how many grams of calcium are in the sample? Interesting. Okay, calcium carbide. 1.5 moles of carbon, and we want to know how many moles and how many grams of calcium. Let's start off with moles of calcium. So, moles of calcium is what we want, right?
Yeah, it says how many moles of calcium and how many grams too.
Yeah, okay, so we can do a grams of calcium after we're done doing the moles of calcium. All right, so how many moles of calcium? If we have 0.15 moles of carbon, 0.15 moles of carbon in this sample, and what has to go down here?
Down there, you need to get rid of moles of carbon.
Very good, so I need moles of carbon up here. Can I go from moles of carbon to moles of calcium?
Isn't that what the chemical formula tells you?
You mean this thing up here?
Yeah, 2 C's for every 1 Ca.
Very good. 2 moles of calcium, carbon for every 1 mole of calcium. So if we have 0.15 moles of calcium, then there's half as many moles of 0.15 moles of carbon, there's half as many moles of calcium. We can solve for that. And then, I guess I don't need to really do it right here. I can just go right here. I can take that answer and go from moles of calcium to grams of calcium, because that's what I said I wanted as well. All right? So 0.15 divided by 2 will give me my moles, and then is it 40 grams of calcium per every mole?
Oh, yeah, that's what the periodic table says.
Very good. Okay, good job. All right, so how many moles of nitrogen in 0.65 moles of ammonium carbonate? And then how many grams of this compound supply this much nitrogen? All right, so what's to the right of our equal sign?
Well, they asked two things.
Which one can you see easily?
Moles of nitrogen.
Good. Moles of nitrogen. From what? What are we giving us to start with?
0.65 moles of ammonium carbonate.
0.650 moles of ammonium carbonate, NH4,2CO3. Now, I knew this because we just worked with it a little bit before, but it's critical that you know what that chemical formula looks like, right?
How would you know if you didn't know it recently?
Well, we would have to look at the polyatomic ion chart and see that we have NH4, and that the NH4s have plus charges, and then the CO3 2 minus, or carbonate ion has a -2, and then we see that we need 2 of these, 2 NH4s for every one of those 2 minuses. Okay?
Okay.
So what goes down here?
You start with moles, and so moles go down there?
Very good. Moles of NH4 to CO3 to grams of, I don't want to go to grams, I want to go to moles of nitrogen. Moles of nitrogen. How many moles of nitrogen are in 1 mole of this material?
Let's see, it's just 2, right?
Yeah, 2 moles of nitrogen for every mole of that material. Very good. So this value times 2 would give me my moles of nitrogen. And then they want to know how many grams of this compound supplies this much nitrogen. So they're essentially saying grams of NH4CO3. And they're just wanting to know how many grams of ammonium carbonate are in that many moles. So I go from moles to grams. Molar mass of ammonium carbonate, was that 106?
According to Wikipedia, ammonium carbonate is a salt with the chemical formula carbon
96.
trioxide.
96.09 carbon trioxide per mole. Okay, good. Good job. Okay, how many kilograms of a fertilizer made of pure ammonium carbonate would be required to supply 1 kilogram of nitrogen to the soil? All right, so question is what? What are they asking us here?
How many kilograms of the fertilizer, kilograms of the ammonium carbonate?
Very good. Of NH4 to CO3. All right, and we're starting with 1 kilogram of nitrogen. That's what we say that we want to have, 1 kilogram of nitrogen. So if I have 1 kilogram of nitrogen, I can go from kilograms to grams of nitrogen. And now why do I want to go to grams?
I'm not sure.
Well, because I know grams to moles easy, right? I know grams to moles of nitrogen. And if I go from moles of nitrogen, I know moles of nitrogen to moles of ammonium carbonate easy, right? NH4,2CO3, right? And then I can go from moles of ammonium carbonate to NH4,2CO3. Oops, this is the NH4,2CO3. I can go to grams of NH4,2CO3. And then I can go from grams to kilograms. That's my 1,000 grams for every kilogram. All right, so I went to moles of nitrogen because I could get moles of nitrogen to moles of ammonium carbonate, right? And I went from moles of ammonium carbonate so I can get to eventually kilograms of ammonium carbonate. Okay, good. So let's see, what's this? Grams of nitrogen to moles?
Isn't that 14?
14 grams per mole. Very good. This one here?
Moles of ammonium carbonate on top and moles of nitrogen on the bottom. Let's see, that's 2.
2 moles of nitrogen for every mole.
Yeah.
Okay, good. How about this one?
Oh, we just did that. That was like 96.1.
That's right, 96.1 grams for every mole of that. That's just the molar mass of the ammonium carbonate, right? And so we got 1 times 1,000 divided by 14 divided by 2 times 96.1 divided by 1,000. And that'll tell us kilograms of ammonium carbonate.